Welcome to Discrete Mathematics. Now, if you've been taking math classes such as calculus, I think you'll find that this will be a nice breather because today we're going to learn something that I believe everybody can understand, even if you don't have some advanced background in math. Today, as you can see, we're going to show that an integer is even. We're going to define this. So, how would you define an integer being even? Well, you might say, well, if you can divide an integer by 2, then it's even, right? 8 divided by 2, we say 8 divided by 2 is equal to 4, so 8 is even because we could divide it by 2. Well, you're not wrong, but we're going to define it in different terms. We're going to say that some integer x is even provided that 2 divides x, and that's what this vertical line means. It means divides x. So we're going to say if 2 divides x, then x is even. Now, what does that mean? In general terms, what does b divides a mean? Well, we say b divides a, provided we can say there's some integer such that a is equal to b times c, and c is another integer. So we'll say b divides a, provided there's an integer c such that a equals b times c. So what does this mean in terms of our even numbers, right? We say 2 divides x means that x is an even number. That means we can write x as x is equal to 2 times some integer, and we'll call this integer a. And this makes sense, right? Let's say if we go back to our example with the integer 8, we say 2 divides 8, thus we'll say 8 can be written as 2 times some integer a, and in this case that integer a is 4, right? So this makes sense so far, right? Now, we've done even numbers. I think the next obvious question would be, well, how do we show that an integer is odd? Well, our definition for an even number is going to be similar to our definition of an odd number. We'll say that some integer x is odd, given x is equal to 2 times an integer a plus 1. And again, this makes sense. Think for a second. What if we had the odd number 9, right? Well, we can say that 9 is equal to 2 times 4 plus 1, right? And you can do this with any odd number you think of. All right, now that we've done these even and odd definitions, how is this going to help us look at more complicated things in math, right? Let's look at that. So say you may have noticed that the sum of two odd integers is always even. Think about that for a second. 3 plus 5, that's 8, right? 11 plus 13, that's 24. You're seeing a pattern. When we add two odd integers, their sum is even. But is there a way we can show that this is always going to hold? Can we show that if we have two odd integers, let's say x and y, show that their sum will be even? Now, well, how do we show that a sum is even? Well, our definition of an even number is 2 times some integer, we'll say a, right? So can we show that x plus y is equal to 2a, right? Well, we have definitions of odd numbers, of odd integers, so let's use those, right? We say x is an odd integer, so we're going to say that x can be written as 2 times an integer b plus 1, and then we'll say y might be the same odd integer, it might be a different one. We're just going to say that this is equal to 2 times some integer c plus 1. And this is equal to 2a. Now, we don't really seem to be any closer to making the left and right side of our equations the exact same thing, but we can still combine some like terms on the left side of the equation, right? We can combine our 1's, so we'll get 2b plus 2c plus 2 is equal to 2a. All right, we got a lot of 2's. Maybe let's factor out a 2 from this left side of the equation, right? When we do that, we get 2 times b plus c plus 1 equals 2 times a. Now we're almost here. Do you think you have a guess of what the next step may be? Well, b, c, and 1 are all integers, right? And the sum of any amount of integers will be another integer, right? If you have the numbers 3 and 4, they equal 7. That's an integer, right? So b plus c plus 1, right? When we add those all together, that is some larger integer. And it might be smaller, we don't know if they're negative, but anyway, it is some integer, right? And how about we just call that integer a? We'll say that b plus c plus 1 equals a. So 2 times b plus c plus 1 is equal to 2 times a. And there we go. We just showed that the sum of two odd integers will always be even because we got it in this form. We got it in the 2 times an integer form. Now, let's look at an example of how useful that definition of dividing can be, right? So say if we have some integers a, b, and c, right? We want to show that if b divides a and c divides b, then c also divides a. Now, let's kind of rip apart these definitions. We're showing that b divides a. That means there's some integer, we'll say x, such that a is equal to b times x, right? That's just the definition of our divide. You can go back to the beginning of the video to review that. So we have that, and we're given that c divides b. So let's say there's some integer y, such that c, or hold on, that's my bad, such that b is equal to c times y. And we want to show that c divides a. How can we do this? Well, alright, let's see. Well, we have a b right here, right? We have b in other terms right here. So why don't we substitute that into our equation for a, right? We'll say that a is equal to c y x. Now remember earlier how I said if we sum any amount of integers, their sum will be another integer. Same holds for the product of integers. Y times x will be another integer, just like 3 times 4 is 12, or 11 times 11 is 121, all integers. So, instead of having this a equals c y x, let's just multiply y and x and say that their product is some integer, I don't know, z, right? And we'll say that a is equal to cz. Now, wait a second. If we say that a is equal to c times some integer z, then that means c divides a. Look at that. We use our definitions of divides to prove something, right? So that's like here, let's do an example of this. If we know that 6 divides, that's not a good example. Yeah, if 6 divides 12, right? We know that it does because we say 12 is equal to 6 times 2. Here, let's write this down. 6 divides 12. We'll say 12 equals 6 times 2. And we know that 3 divides 6, right? We know that 3 divides 6 because 6 is equal to 3 times 2. Given these two facts, we know that 3 is also going to divide 12. We know that 3 divides 12, and we can show this. 12 is equal to 3 times 4. Look at how useful that was. Now, I want to go over one last thing real quick because I keep saying the word integers. Now, what are the integers? The integers are a set. They belong to a set, and this is our little notation for them. It's a z with like another line right here. It's kind of hard to draw. But yes, we say that the integers are this set z, right? And sets we use curly brackets for, and this is what the set of all integers looks like. We'll use a little dot, dot, dot. I'll say -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. So you can see it's all these positive and negative whole numbers from negative infinity to positive infinity and including 0. 0 is an integer. So now that we've gone over that, we've learned even numbers, odd numbers, what divides means, and what the integers are. If you made it to the end of this video, thank you for watching. I really appreciate it, and I hope you learned something.